Hello, wonderful carrots. In this video, we're going to be talking about time complexity, and we're going to be taking it back all the way to the very beginning. Not this beginning, more like this one. Let's pretend that today was the first day you've heard of time complexity. Well, the fundamental question is, what is time complexity? To begin answering this question, we'll start by talking about algorithms, or to be specific, what is an algorithm? An algorithm is any set or collection of steps that are designed to solve a specific problem or perform a specific task. That's pretty straightforward, right? So what does this have to do with time complexity? Well, time complexity is about expressing the relationship between the number of operations or steps an algorithm will perform and the size of the input that is given to it. What exactly does this mean? Well, it means this. We're looking at the number of steps an algorithm will perform as a function of the size of the data that is passed to it. So as the size of the data increases, what happens to the number of steps that the algorithm must perform? Does it remain constant, or does it increase in a linear fashion, or does it increase quadratically, which you can't really see in this graph, but we'll come back to that later. Now that you have a basic idea of what time complexity is about, let's talk about primitive operations. Primitive operations are operations that are pretty simple and straightforward. They're performed almost instantly, and we say they take constant time. We count the number of primitive operations, or steps, and use this number t as a high-level estimate of the time complexity or running time of an algorithm. So we count the number of primitive operations within the body of the algorithm, such as a function or method, and we use this number to estimate its running time or time complexity. Let's have a look at examples of primitive operations. In the first line, we can see that initializing a variable is a primitive operation. In the second line, performing a comparison between two different values is also a primitive operation. Initializing an array with a specific set of values is also a primitive operation, and so is array indexing. That means accessing a specific index of an array. In the method, we can see that performing an arithmetic operation is a primitive operation, and so is returning a value. Now that we have an idea of primitive operations, let's talk about constant time. An algorithm is a constant time algorithm when the number of steps it performs remains constant regardless of how much data or regardless of the size of the data that is passed to it. It could be 100 steps, it could be 2 steps, and it could be 1 step. The point is, it must remain constant. Let's look at an example. In this method, we're given some array and perform two primitive operations. The number of steps we're performing in this algorithm is not dependent on the size of the array. In other words, regardless of the size of the array, it will always just be 2 steps. So we write this as O of 2, which is then simplified to O of 1. This could be O of 100 steps. The point is, it will always be simplified to O of 1 because it is a constant time algorithm. Now that we understand constant time, let's talk about linear time algorithms. An algorithm is linear when the number of steps in the algorithm increases as the data increases. That means the number of steps is dependent on the input or the input size. Let me give you an example of a linear time algorithm. Let's look at this example. We have a method that takes in some array, and for every value of this array, it performs two primitive operations. If you recall from earlier, array indexing is a primitive operation that takes constant time. If we have an array that is of size n, we must index n times to access all elements of the array. And we are performing two primitive operations within this body, which gives us 2 times n, where n is representing the size of the array. This then we can write as 2 times O of n, which is then simplified to O of n because we actually don't care about the constant. So this is a linear time algorithm. Now, let's talk about quadratic time. An algorithm is quadratic when its performance is proportional to the squared size of the input data. This will happen when we nest over multiple iterations of a set of data, or we have multiple nested for loops. Let me give you an example of a quadratic time algorithm. We have a method that takes some array and performs 2 nested for loops over the elements of this array. Within the body of the nested for loop, we perform some number c of primitive operations. Given the size of this array is n, we have c times n, where the two n's are representing the number of indexes that are performed within the for loops, and c represents the number of primitive operations within the body of the nested for loop. This can then be simplified to c times n squared. which then can be represented by c times O of n squared, and then simplified to O of n squared, because again, we do not care about the constant. You can imagine as the size of the data that is passed to this method increases, it becomes less and less efficient. That is, the amount of steps it must perform is proportional to the squared size of the data. This is why quadratic time complexity is actually quite bad, and we like to hope that we aim for better time complexity, such as linear time or log n time, which we still haven't discussed. Let's have a quick recap. O of 1, or constant time, is the most efficient. We're basically cruising, but it is an unrealistic standard for when we're dealing with more complicated tasks or problems. O of n is still a winner. It is a more realistic standard when we're dealing with more complicated tasks, but it is still quite efficient. O of n squared is the tough stuff. This is because it isn't very efficient. As we deal with large amounts of data, our algorithm will become less and less efficient, and we hope to aim for better time complexities. Here's a big O cheat sheet from the web. It shows you the different complexities and their relative rating. O of n factorial is the least efficient, and O of 1 is the most efficient, shortly followed by O of log n, and then O of n at the top. To put your newly found knowledge of time complexity to a test, here are some exercises. Please feel free to pause the video and give them a go. Okay, I'm about to show you the solutions. Here are the solutions. For the first method, we're given an array. We have a for loop that forms 25 iterations. Regardless of the size of the array, the for loop will only always iterate 25 times. For this reason, this is a constant time algorithm, or O of 1. For the second method, we're given an array, and for every value of this array, we perform 25 iterations. This is equal to 25 times n, where n is the size of the array, which is then simplified to O of n. This is a linear time algorithm. Please note that I didn't take notice of the two primitive operations that are performed in the body of the nested for loop, as they prove to be irrelevant. In the third method, we're given an array and perform two nested for loops. In the body of the nested for loop, we perform some number of primitive operations. Given the array size is n, this is n times some constant c, which is then simplified to O of n squared. This is a quadratic time algorithm. This brings us to the end of this video. Please like, subscribe, and comment below to give me feedback on the content. I look forward to seeing you next time. Till then, stay chill.